viewers, we are TCU students from BSCS A21 and here are my group mates.
Hello, I am Maria Aminel P. Labadan. Hi, my name is Marian D. Musyares.
Hi, my name is Mark Erzadem.
Hi everyone, I'm Manel A. Pandilio.
And I'm Emmanuel C.P. Salvo and we are here to present to you proofs on corresponding parts of congruent triangles are congruent or CPCTC and Descartes Theorem.
Here is our CPCTC proof number 1. I have a triangle and I'm going to name these points as point K, point J, point H, and point I. Our main goal is to prove that the parts of the triangle are congruent. But before that, we must prove that the two triangles are congruent. And here's the given. Segment HI is congruent to segment HK. Segment HJ is perpendicular to segment KI. CPCTC proof number 1. Here are the statements. Segment HJ is perpendicular to segment KI. Based on the reason given. Number 2, angle HJK and angle HJI are right angles. Based on the reason, definition of perpendicular lines. Number 3, triangle HDK and triangle HJI are right triangle. Based on the reason, a right triangle has a right angle. Triangle HJK is congruent to triangle HJI. Reason, hypotenuse leg postulate. And the last, statement number 7, segment KJ to segment JI. And the reason is congruent, corresponding parts of congruent triangles are congruent.
that segment ML is congruent segment MN. Given segment OM bisects angle LMN. Angle LOM is congruent angle NOM. Here are the statements and reasons of CPCTC proof number 2. Statement reasons. Statement number 1. Angle LOM is congruent to angle NOM. Reason based on the given. Statement number 2. Segment MO is congruent to segment MO. Reasons, reflexive property of congruence. Statement number 3. Angle LMO is congruent to NMO. Statement number 4. Triangle LMO is congruent to triangle LNMO. Reasons, ASA postulates. Statement number 5. Segment ML is congruent to segment MN. Reason, CPCTC.
Hello, we're here to prove the Descartes Theorem, the kissing circles. We have the 4 circles. The first circle is the alpha, next is the beta, and the third one is the gamma 0. And the last is the saddest circles, where in the saddest circles we have gamma sub 1, gamma sub 2, gamma sub 3, and gamma sub 4. In Descartes Theorem, we have formula 2 times e sub 1 squared plus e sub 2 squared plus e sub 3 squared plus e sub 4 squared is equal to e sub 1 plus e sub 2 plus e sub 3 plus e sub 4 squared. Where in e sub I and I is equal to 1, 2, 3, 4 are the bends reciprocals of the radii of 4 mutual tangent circles. If the first 3 circles found a curvilinear triangle containing the fourth or e sub 4, the relation may be used in Steiner's unsymmetric form, and where e sub 4 is equal to e sub 1 plus e sub 2 plus e sub 3 plus 2 and square root of e sub 1 times e sub 2 plus e sub 2 times e sub 3 plus e sub 3 times e sub 4.
And for our continuation, let's go to the derivation of cosseter. As cosseter indicated, delta is equal to the square root of E1 times E2 plus E2 times E3 and plus E1 times E3. The formula is geometrically meaningful. It is the bend of the circumcircle of the curvilinear triangle determined by the circles of bend E1 and E3. With this change of notation, Stein's formula assumes the more attractive form. And here's the formula for Steiner. Cut.
Still, I continue the Descartes Theorem. These are the derivation formulas. Generalized formula is gamma equals gamma sub 0 plus 2 times n times delta plus n squared times alpha plus beta. Proof beginning with Descartes circle theorem for circles with bend. Alpha, beta, gamma sub I minus 1 and gamma sub I. 2 times alpha squared plus beta squared plus gamma sub I minus 1 plus gamma sub I squared equals alpha plus beta plus gamma sub I minus 1 plus gamma sub I squared. Similarly, from the 1 minus 1 stage, 2 times alpha squared plus b squared plus gamma sub I squared minus 2 plus gamma sub I squared minus 1 is equal to alpha plus b plus gamma sub I minus 1 plus gamma sub I squared. Subtracting and dividing by gamma sub I minus gamma sub I minus 2. 2 times gamma sub I plus gamma sub I minus 2 is equal to 2 times alpha plus beta plus gamma sub I minus 2 plus 2 times gamma minus 1 plus gamma sub I. Rearranging and writing the resulting equation for I equals n minus 1 to 2. 2 times alpha plus beta minus gamma sub n minus 2 plus 2 times gamma sub n minus 1 minus gamma sub n equals 0. 2 times alpha plus beta minus gamma sub n minus 3 plus 2 times gamma sub n minus 2 minus gamma sub n minus 1 is equals to 0. 2 times alpha plus beta minus gamma sub 0 plus 2 gamma sub I minus gamma sub 2 equals 0. Multiplying these equations by 1, 2, 2, and minus 1. And adding, we obtain n times n minus 1 and alpha plus b minus n minus 1 plus n times gamma sub 1 minus gamma sub n equals 0.